The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
So you all should have these handouts ready to go now. So let's review where we were last week. So everyone can settle down a little bit. You can discuss about who wants to be the top chemistry major later on after class is over. All right, so octahedral case. So here is our octahedral molecule. And again, crystal field theory is just an explanation for things that are observed experimentally. So it's a fairly simple theory, and if you go on to study chemistry, and you'll take more inorganic chemistry later on, you'll learn about more complicated theories, but this is really simple. So this simple theory just thinks about each ligand, each small molecule like NH3 group bound to a metal, the metal is in the center position, that each ligand it considers as a negative point charge. And so then the theory looks at whether that ligand as a negative point charge is pointing toward one of the d orbitals. So you need to know about the shapes of the d orbitals, and you need to know about the shapes of the coordination complexes, and then you need to just ask yourself, is that ligand pointing toward directly toward a d orbital? If it is, then it'll be destabilized. If it's not, then those orbitals will be stabilized. And so you're talking about the stabilization relative to an imaginary spherical crystal field where ligands are just sort of everywhere all around the center metal. So you consider that as sort of your standard case where all of the d orbitals have the same energy. But then when you consider those ligands as negative point charges in particular locations, some d orbitals then get destabilized and other ones get stabilized in terms of energy. So in the octahedral case then, and here's our little cartoon for the octahedral case, where one ligand, there are ligands along the z-axis, ligands along the x-axis, and ligands along the y-axis. And so if you look at dx squared minus y squared, you see that the ligands will be pointing directly toward these d orbitals, because ligands are coming in along y and along x, and so there will be a lot of destabilization. For z squared, you have ligands pointing directly toward those orbitals as well along the z-axis. So these have large repulsions due to the negative point charges. Those negative point charges are heading right toward those d orbitals. And these two are degenerate with respect to each other. They have the same energy, the same amount of destabilization. And these are destabilized compared to this other set of d orbitals. And in this set of d orbitals, none of the orbitals are on axis. They're 45 degrees off axis. The negative point charges are on axis. So there's not as much destabilization. The ligands aren't pointing directly toward any of these d orbitals. So you have smaller repulsion. All of these three are of the same energy. They're degenerate. And they're all stabilized compared to this set. So that's what we talked about last week. And we also talked about how you can draw an octahedral crystal field splitting diagram. And here's the average energy of the d orbitals with this sort of spherical crystal field where ligands are everywhere. And so when ligands are everywhere, all of the d orbitals have the same energy. But then when you put the ligands in their locations, in the octahedral geometry framework, then these two sets of orbitals, dx squared minus y squared and dz squared, are up in energy. They're destabilized. And these three go down in energy. And the overall energy of the system is maintained. So here's the crystal field splitting energy for the octahedral case, O for octahedral. And so it's split. Two orbitals go up in energy, so they go up by 3/5. Three go down, so they go down by 2/5 to maintain the overall energy of the system. So that's what we talked about last time. And I just wanted to review it because we're going to go on and talk about other types of geometry. And of course, remember that exam 3 is on Wednesday. extra problems are posted. I will mention that I actually posted the original exam last year, and the exam that people took was slightly easier than the one I posted. I did that actually by mistake, but it turns out that if you do that, the exam that's posted is a better indicator of how well you'll do on this next exam, because the final exam, the third exam last year, was a bit too easy, i.e. too easy means that the sort of outstanding category was like 98 and above, and if you got a 97, then that was no longer outstanding. So whether you got 3 significant figures wrong or 2 made some difference in your grade. That clustering I don't like. I like to have the average such that people's performance on the exam really indicates more how well they know the material. So the exam that's posted is actually the better review. So even though that was an accident, I'll pretend I did it on purpose because it's a better thing. So extra problems on. So today we're going to finish up crystal field theory and then talk about the relevance of crystal field theory. And the relevance comes into explaining the colors of these transition compounds. So they have these compounds with metals have some really spectacular colors. And you can explain or rationalize some of these colors by this really very simple theory. So that's fun. And you can also explain some of the properties and magnetism of these compounds by this fairly simple theory. Okay, so let's look at the tetrahedral case now. So here we have our tetrahedral molecule. I'll try to kind of hold it up as it's displayed on the board. So in this case, we have 2 ligands up, one coming towards you, one going back. So coming towards you and going back. And then we have 2 ligands in the plane of the screen. And in this case, the convention is to draw the z-axis coming down here, and the y-axis is kind of coming in from the side, and the x-axis is coming out towards you here. So that's what this picture indicates. So the crystal field splitting energy tends to be smaller than the octahedral crystal field energy because none of the ligand point charges are really pointing toward any of the d orbitals. And let's just take a look at all the d orbitals and consider then which ones are going to have more repulsion than other ones. So if we go through and take a look at it, and I've tried to indicate, so here are our tetrahedral cases, and here are our 5 d orbitals. And these little lines of the negative charge and the arrow is sort of a rough approximation of how those ligand point charges are going to be coming in and pointing toward the d orbitals if they're coming in with this tetrahedral geometry as drawn. And so you can see for the dx squared minus y squared, none of those ligands are pointing right at any of the d orbitals. And they're definitely not for the dz squared either. A little bit more here, but again, not exactly pointing toward them, although this picture looks like it is a little bit. But again, it's closer here, but not exact. So the result of this is that there's more destabilization down here than there is up here. So it turns out that this is then opposite of the octahedral case that we just talked about. In octahedral, these are the ones that are most destabilized. In tetrahedral, these are stabilized compared to the others. So it's flipped exactly around. So again, there'd be more repulsion between the ligands as negative point charges and the orbitals that are 45-degree off-axis, because here the ligands are off-axis, and also the orbitals are off-axis. They're not directly pointing at each other, but it's definitely worse down here. These guys are really far away from those ligand point charges. So these two will have the same energy with respect to each other. They will also be degenerate as they were before. And these 3 have the same energy with respect to each other. They are also degenerate. So then we can draw what the diagram will look like for the tetrahedral case. So again, here was the octahedral case. Now this is the tetrahedral case. And so we have the splitting energy, which is the energy that splits the orbitals based on these negative point charges compared to this theoretical spherical crystal field. And we also have a tetrahedral crystal field splitting energy. So that's drawn here. Now the first thing, which I emphasized that I'll point out again, is that these guys are flipped around. So instead of being destabilized as they are in the octahedral crystal field, the dx squared minus y squared and dz squared are now stabilized compared to the other orbital set. So they've switched positions. These, instead of being stabilized, are now more destabilized. So it's a direct switch. There's also a little change in nomenclature here. So you can still refer to this orbital set with the term E, but instead of EG, we have E. And I'll just point out that the book calls this E2, and sometimes it calls it E. It should just be E, but this is kind of a small point, but I don't want people to get confused by that. And instead of T2G, we have T2 up here. So basically, the G term is gone in this case. And you'll learn a lot more about that if you go on and take more inorganic chemistry. So these are flipped. What else is true? Well, the other thing that's true is that this splitting energy is much smaller in the tetrahedral case than it is in the octahedral case. So here there's a much bigger distance between the orbitals. Here it's a much smaller distance. And that is because in the octahedral case, there are ligands pointing directly at the d orbitals. So in this framework for octahedral, there are ligands right along z, along x, and along y. And so they're along all of the orbitals, pointing directly toward the orbitals. In the tetrahedral case, they're not really pointing directly toward. They're closer to some than to others, but it's not as direct. So a result of that is that there's just not split that much. There's not such a huge difference between the energy levels of the d orbitals in this case. So what does this mean? Well, it means that a lot of tetrahedral complexes, because the splitting energy is small, a lot of them are called high spin. And we talked about this last Monday, that in high spin, you have the maximum number of unpaired electrons. And because this, and the purpose of this, you can just assume that if you have a tetrahedral complex, it will be high spin. So that will come into play when you figure out how to put your electrons into this diagram, whether you put them in singly to the fullest extent possible without pairing, or if you start to pair. So in this case, you can put them in singly to the fullest extent possible. Okay, and as I mentioned before, the overall energy of the system is maintained. So in this case, you have two orbitals that go up in energy, so they go up by 3/5, three that come down, so they come down by 2/5. In this case, you have three going up, so they'll go up by 2/5. And you have two going down in energy, so they'll go down by 3/5 to maintain the overall energy of the system. Oops. Okay, so that's the tetrahedral case. So now let's consider square planar. So here we have our square planar molecule. And we have ligands along the y-axis, ligands along the x-axis pointing out towards you, one and one going back behind. And z then is coming up and down in this plane. So with this ligands along y and along x, which would you predict, which orbitals do you predict would be destabilized the most? I heard dxy, that's one. What else? dx squared minus y squared, right. So those two. So the ones that don't have the z component in them. So there's really not much destabilization along Z. There are no ligands along Z. So orbitals that have amplitude along Z are not as affected. So the ones that will be most affected are the orbitals that have component in the X and the Y direction where the ligands are. So now we can consider the d orbitals and talk a little bit more about this. So if we look at these two sets of orbitals now, here, as you correctly predicted, there'll be lots of repulsion. So the ligands are pointing directly at these d orbitals. The ligands are on axis, the orbitals are on axis. It's a direct hit. So there's a lot of destabilization. And this one now is going to be destabilized compared to all other ones. So it's going to be by itself the most destabilized orbital. dz squared doesn't really have much destabilization at all. In fact, it'll be stabilized. There's no ligands along Z, so there's no real repulsion of the ligands to dz squared. So it's going to be a lot less than for this guy, and also less for than dxy. So we can draw this now, put in two of the orbitals. This one is going to be way up. It's going to be by far the most destabilized. So it's going to even go up from where it was in the octahedral case, whereas dz squared, which was up here, degenerate with dx squared minus y squared in the octahedral case, is now going to drop way down. So these aren't equivalent at all anymore. And so this makes sense. The difference between the octahedral geometry is that there were ligands along Z. Now the ligands along Z are gone in the square planar case. So there's a big difference between these two orbital sets in terms of energy. Now let's look at these three. So this one, as people correctly predicted, is going to have a lot more repulsion than either of these, because we have the orbitals have maximum amplitude along x and y. They're actually 45 degrees off x and y, but still we don't have anything in the z component here. So this will be destabilized compared to these two, and these two are stabilized compared to the d orbitals dxy, dx squared minus y squared. So now we can go and take a look at where these would be positioned approximately. So if we look at this one, it's not nearly as destabilized as this one, but still it's a bit destabilized and above this. This one is lower in energy. And if you consider the difference here, again, dx squared minus y squared, the ligands are pointing directly at the orbitals. It's on axis. Here, it's 45 degree off axis, so it's not as destabilized, but still it's up above where it was in the octahedral case. And then finally, these two guys are going to be stabilized compared to this theoretical spherical crystal field. So they're going to be somewhere down here. So the big points here then are that when you get rid, compared to the octahedral case, you get rid of the ligands along Z. This guy shoots up. This one comes down. It's stabilized. The other d orbital that has maximum components along x and y, which is where those ligands are, goes up a little. So these three are all sort of stabilized. These two are destabilized, but this one is destabilized quite a bit more. These also will have, you can draw sort of splitting energies here, but that's just too complicated. We're only going to do this with the octahedral and tetrahedral case because there's many more layers here, and these are a little bit different. So all you need to know is sort of this relative ratio. This is the most destabilized. This is next. These guys are stabilized. That's all you need to know. We're not going to draw splitting energies going up by 1/5 and things like that for this case. But you'll hear about this more if you go on in chemistry. So what I expect you to know is to be able to rationalize. If you know something about the shape of a molecule, suppose you had a linear molecule along the z-axis. a good test question might be, which orbitals would be the most destabilized if you're linear along Z, for example. So you should be able to think about the shapes of the d orbitals, think about the shapes of the molecules, and predict the orbitals with the most stabilization and the most destabilization, and to be able to explain your rationale for predicting these splitting diagrams. Now we're going to talk about how these diagrams and thinking about the splitting of the d orbitals can explain the beautiful colors of these coordination complexes. So let's go back to the octahedral case for a minute and talk about two different octahedral complexes. So we have iron plus 3 in two different complexes. We have a high spin state with iron and 6 water ligands, and a low spin molecule, coordination compound, with iron and 6 cyanide ligands. So the first thing you're going to do if you're going to be talking about the splitting is to figure out how many electrons you're talking about, or come up with the d electron count. So let's do that. So if we have iron with 6 water ligands, the overall charge on that is 3 plus. So what is going to be our, and this is on the board too, but what will be the oxidation number of iron? Plus 3. This is 0. And so it all has to equal plus 3. So then the D count is going to be equal to, I'll put up a periodic table. So the D count will be equal to what? 5, right. So we look up the group number is 8 minus 3 is going to be 5. And our other iron complex will be the same. So this one has a charge of minus 3. Cyanide is what? Minus 1. So iron would also have to be plus 3 to get the correct overall charge. So our D count over here as well is going to be D5. So we have the same number of electrons that we need to put into two different diagrams. So we have one, this is our high spin case. And so we can draw the crystal field splitting diagram for the high spin. And put in our orbitals. dx squared minus y squared, dz squared. We have our octahedral crystal field splitting energy. We're going up by 3/5 and down by 2/5 for these compared to this theoretical crystal field. And then we have our low spin case. And again, let's see. So in our low spin case, we have a larger splitting energy. And again, some are going to go up by 3/5, and these three will go down by 2/5. All right, so now we need to put in our 5 electrons. So how am I going to put them in here? Will I fill up all of the different energy levels with 1 before I pair, or will I start to pair in the lower first? we're going to put them in everywhere first. So we'll put all 5 electrons, we'll put 1 in each of the orbitals. So I'm going to place them singly in. And that's because in this case, the splitting energy is small. And since it's small, it's less than the pairing energy. So the pairing energy is the energy required to pair up these electrons. There's a certain amount of repulsion. All of the electrons would love to be alone in their orbital. They'd prefer not for you to put another electron in. So there's a certain amount of energy required to do this. If the energy level between the d orbitals is small, then it's, you put them all in singly and don't pair until you absolutely have to. And this is referred to as the Highspin case, where you have the maximum number of unpaired electrons. So in this case, we have a large energy. So that energy then is greater than the energy required to pair, PE, or the pairing energy. So now we're going to put them all into the bottom until we have to go to the top. So we'll first start out putting them in singly, 1, 2, 3, and then we'll start pairing 4, 5. So now we fill up this bottom set. I should put in the T2G and the EG labels. So we'll put them in this bottom set in T2G until we have to go up to EG, because this is a big energy difference, and you don't want to do that until you have to. All right, so now we can look at the d electron count. So where the electrons are. So here it's T2G3. There are 3 in the bottom. And in EG, there are 2. And over here in T2G, we have 5. There's none in EG. So those are our d electron counts. And then we can calculate the crystal field stabilization energy, which shouldn't be confused with the splitting energy. So this considers how much stabilization you have as a result of the fact that the d orbitals are split in energy. So in this case, you want to count up how many are in the lower energy levels. So there are 3 down here. So 3 times minus 2/5 the octahedral crystal field splitting energy, and you have 2 above, so 2 are up in energy by 3/5. And so what does that equal? 0. And over here, then, you have 5 that are down in energy. So you'd have minus 10/5 the octahedral crystal field splitting energy. And sometimes, in some books, it also includes, there is some energy associated with pairing. So occasionally, you'll see this written as 2PE, indicating that there are 2 sets with paired electrons. So there's some energy associated with that. So it's not as fantastic a situation as it looks like, that there's lots of stabilization where the other has 0 stabilization, 0 destabilization. It's just about the same. But there is some energy associated with this. So sometimes you'll see that. And you only need to indicate that if it's asked for. And I think your book doesn't ask for it, but just so you're aware. All right, so that's kind of a review. We talked about these things on last Monday, but I just wanted to go through it again, because now you need to see how this relates to colors. Okay, so we have to introduce this idea that the relative ability of certain common ligands to split the d orbital level is what's meant by this spectrochemical series. So which ligands there are, in one case water and cyanide, causes a difference. And a strong field ligand, and we talked about this a bit on last Monday as well, produces large energy separation. So over here we have a large energy. So this would be a strong field over here. So it's strong. It splits those d orbitals a lot. And a weak field ligand produces a small separation. It's pretty weak. It can't really split those d orbitals very much. It's weak. So this would be a weak field case over here. So there's not much splitting between the d orbitals. So here are some various ligands and how they fall into this series. And you need to know this for the test, only these sets of ligands. So there are 3 in the sort of weak field category, 3 in the intermediate category, and 3 in the strong field category. So when it's a weak field ligand, you're going to have the small splitting as shown here, and therefore you'll have a high spin system where you have the maximum number of unpaired electrons. If you have a strong field, you have a large splitting, and then you're going to have a low spin system where you have the minimum number of unpaired electrons. So in the example that we just had, we had this as high spin. So it's actually kind of an intermediate, but it was determined to be high spin experimentally. The intermediate ones are a little harder to predict. These will be strong field. These will be weak field. These are harder to predict. Cyanide, according to this list, is the strongest field ligand. So that makes sense that that was then a low spin system. So colors. So colors are going to depend on what photons are absorbed and the energy level it takes to get to that excited high energy state. So here, it's a very small difference. Here, it's a big difference. So you would need to absorb differently and then also transmit differently to excite those electrons. And that's going to give rise to the different colors. So let's just take a look at this. So now we're reviewing back to the first half of the semester where you saw this. So we have the energy of the absorbed light is equal to Planck's constant times the frequency. And so we're back here again. We're talking about splitting energies between the d orbitals, the amount of energy to excite an electron from one set of orbitals to the higher set of orbitals. So we're back here. But now we're going to have a little bit of a difference in that we're going to add another equal sign and say that that energy then is going to be, in this case with the transition metal complexes, octahedral coordination complexes, is equal to this octahedral crystal field splitting energy. So again, we're going to be talking about exciting electrons here up to here. And so that depends then on what the energy difference is between these sets of orbitals. So we've seen this before, and now we're just adding this new term on the other end, the octahedral crystal field splitting energy. All right, so this we also saw in the first half of the course. So if you have a high frequency of light is absorbed, the wavelength of the absorbed light is going to be short. And that's that equation, which was, I think these two equations were equations you needed to have memorized. They weren't on the equation sheet. That indicates that they're of really fundamental importance. And then the color of the transmitted light is complementary to the color of the absorbed light. So here, we need to think beyond the first half of this semester, back to probably kindergarten. When did you first learn about complementary colors? Second grade? So I actually was talked into putting something like this on the exam so that you wouldn't have to have that material memorized. But anyway, here are your complementary colors. So if you know something about the color of the transition complex, you can go back and calculate and estimate. If you're given actual numbers, you can calculate what the splitting energy difference was. Or you can approximate whether it's going to be small or large, depending on the colors that the complexes have. So let's take a look at some examples here of two different coordination complexes both octahedral. So first we have to figure out the oxidation number. So again, this goes back to the last unit on oxidation reduction. We'll have on the useful for the exam on Wednesday. So the number here, you're going to have +3 for both of these guys. So this is 0 and that's 0. The overall charge is +3, so chromium has to be +3 in both cases. Then when we do the d electron count, we have to find chromium on our periodic table, look up what group it's in to calculate the d count. So we have that here, and we have a D3 case. What does CN stand for? Coordination number. And so what's the coordination number in this case? 6? Right. So there's 6 things here, 6 things coordinated. And that's not to be confused with the steric number, which we talked about last Wednesday. So the type of ligand here, water was what? What type of ligand in terms of weak to strong field? It was intermediate. And over here is stronger. So these guys are actually not that far apart from each other. Water was sort of intermediate. It is at least weaker than NH3. NH3 was in the strong category, so it's at least stronger than water. They're not that far apart from each other, but this one should be a stronger field ligand than this one. So if we consider a weaker field system and a stronger field system, is this going to make any difference to how we put in electrons this time? No, it won't, because we only have 3. So we would put them in the bottom regardless. So the issue is when you get to the 4th one, when you have the 4th electron, you have to decide if you're going to put it up here or if you're going to pair. But there are only 3. So the diagrams look the same. But even though the diagrams look the same, these compounds are going to have different properties because they have different splitting energies. And so the amount of energy required to bump an electron up here is going to be different than up here. And so you'll have different colors as a result. So let's take a look at that. So again, this is intermediate, so this is smaller. This is stronger, it's larger. It doesn't affect how the electrons go in, but it does affect the property of the compound. So let's go through this and see what this means. So water then is weaker. It means the splitting energy is smaller. So if the splitting energy is smaller, that means you have a lower energy, a smaller energy between them, and a lower frequency that'll be absorbed. In this case, this is a strong field ligand, so you'll have a larger energy and a higher frequency that is absorbed. So over here, if we have the lower frequency absorbed, we have a longer wavelength absorbed. For the stronger field case, we have somewhat of a higher frequency absorbed, so we'll have somewhat of a shorter wavelength absorbed. And then the color of the transmitted light is complementary to the color of the absorbed light. So here you're going to have a transmitted light with a shorter frequency. You had a shorter wavelength. You had a longer wavelength absorbed, so you'll have a shorter wavelength transmitted. And this compound is, in fact, violet. Over here, you're going to have the shorter wavelength absorbed. So the transmitted light will be complementary to that, and we'll have a longer wavelength. And this compound is, in fact, yellow. So if we look again at the colors and their wavelengths, this complex with a strong field ligand is yellow, and the one with an intermediate field ligand is violet, somewhere down in here. So even though water and NH3 are close to each other, the one that's stronger definitely has quite a distinct color from the one that's a bit weaker. And unless you're given numbers, you can't predict exactly which color. You can just rationalize the relationship. So if you were told this is yellow and this is violet, tell me why, you would say this is a stronger field ligand than this one. So that's the kind of thing you can do. But if you're given numbers, and on problems, and on the final you may be given numbers, you can actually come up and calculate back and forth from the splitting energy to the color that you predict, from a color back to the splitting energy. So what things would be colorless? Which kind of coordination complexes will be colorless? And why would it be colorless? This is where things written in your handout can be read back to me. Unless you know, but it's good to think about it a little bit. Okay, so if you filled up all your d orbitals and there's no room for things to move around, when it's not possible to have a d to d transition, so you filled up everything, so you're not going to be able to do this transition from one set of d orbitals to another one, then you have colorless. So here are some examples of things that will be colorless. And let's just prove that that would be true, that those are in fact filled. So we have zinc and cadmium. So if we look, zinc and cadmium are in group 12. So 12 minus 2, they're both have oxidation numbers of +2. So 12 minus 2 is 10. You have a D10 system. This one's also going to be a D10 system. So you're going to have all 10 electrons already in. And so you're not going to have these transitions. And so these, in fact, are colorless. Zinc is a really important metal in biology. And it plays structural roles. It can play catalytic roles. It's a very important metal. And often when biochemists are trying to figure out how a protein works, they won't realize it's a zinc-containing enzyme because the protein won't have any color. In contrast, there are proteins and cofactors in metals that have a lot of color, and then you can actually, as you're purifying the enzyme, it'll have this bright orange or red color, and you realize it has some metal cofactor in it right from the very beginning. Okay, so just to go through then and sort of summarize this whole procedure, if you're on this end with the ligands and the weak field ligands, then you're going to have a small splitting. Weak things can't split much. They don't have enough strength to really split those d orbitals apart. You'll have a high spin system in this case, maximum number of unpaired electrons. In terms of the complexes, then they'll absorb low energy photons, low frequency, long wavelength, and then they will transmit high frequency or short wavelength. So they're going to be in this violet, blue, green end of the spectra. And let me just put this one up. And actually, let me just put all these guys up. So they'll be on this end of the spectra. Again, it's all based on these two equations. So if you have a small splitting, small energy, you're going to have a low frequency, and then you'll have a long wavelength for absorbed, and the complementary for the transmitted. If you're strong field, you'll have a large splitting energy. It'll be low spin, minimum number of unpaired electrons, and you'll have a situation like this. You know, here you fill them up to maximum extent. Here they're low spin, maximum paired. So then you'll have the complementary. If you have short wavelength absorbed, you'll have long wavelength transmitted, and you'll be on this end of the spectra. So you would expect yellow, orange, or red in this case. So you can make predictions. If you know something about the ligand, you can predict the color of the coordination complex, or at least rationalize the color of the coordination complex. So just to show you sort of a real example, these are all octahedral complexes with cobalt. And you can see the colors are really dramatically different. So depending on the ligand to the cobalt, you can really get this beautiful range of colors associated. And one of the courses that's offered during IAP that Dr. Schrenk teaches, you go through and actually do some of these experiments and see these colors. And so it's a little lab component that complements nicely this part of the course as well as a few other parts of the course. So those are of these coordination complexes. And cobalt is also in a vitamin. Can someone tell me what vitamin cobalt is in the center of? What's my favorite vitamin? Yes. So these are colors of B12. So this is protein bound to different forms of B12. So there's actually different ligands to the cobalt in these three cases. And these are the actual colors. It's really spectacular, the colors of these. And these are crystals of the protein, so the colors are really very rich. So when you're doing experiments on a B12 system, you know something about the form of B12. If you've done some damage to your B12, you know it by actually looking at the color of the molecule you're working with, of the crystals or the protein you're working with. Okay, so very fast then, magnetism. So compounds that have unpaired electrons are paramagnetic, attracted by a magnetic field, and ones where they're paired are diamagnetic, so they're repelled by a magnetic field. So you can figure out something about the geometries often of your compounds by figuring out whether the compound is paramagnetic or diamagnetic. All right, well, how would you do this? Well, if, for example, you had a nickel 2+ system in an enzyme, so you have a D8 center in your enzyme, and it's found to be diamagnetic, you could ask the question, can I guess then whether it has square planar geometry, tetrahedral geometry, or octahedral geometry? Because it is diamagnetic. Can I figure out the geometry knowing that fact, knowing about unpaired or paired electrons? In this case, we'd have to have it's diamagnetic. All the electrons have to be paired. So here are our splitting diagrams for all three cases. Let's look at octahedral. Again, we have to put 8 electrons in. Here are 8 electrons. Does this matter if this was weak field or strong field in this case? Which is it? Can you tell? Same. Right, because you would put in electrons, whether you put them in 1, 2, 3, 4, 5, 6, 7, 8, or put them in 1, 2, 3, 4, 5, 6, 7, 8, it's the same. So this could be either. Notice we have unpaired electrons, so this cannot be the geometry of this unknown center. What about square planar? Let's put them in starting at the bottom. So we'll put them all in, keep going, just put them all in. There are 8. So it didn't really matter too much the order I put them in down here. The important point is I really didn't want to put any in here until I had to, because this one, if you recall, is really destabilized compared to the rest. All right, so these are all paired up. And let's look at tetrahedral. Tetrahedral tends to be what kind of spin? High spin, because the splitting energy is small, because you don't have ligands pointing directly at the d orbitals. So we can put them in a high spin fashion until we're done. And that's our system. This is small splitting energy, and down here. So we have unpaired electrons here. So this is paramagnetic, this is paramagnetic, this is diamagnetic. So then you could predict that the nickel in the enzyme must be square planar. It can't be this, and it can't be that. So it tells you something about the geometry. And I'll tell you that there are 2 square planar systems, at least, in enzymes of nickel, and people predicted it using similar kinds of techniques to what you just learned about in freshman chemistry. Okay, good luck on the exam on Wednesday.